So we got this girl, she's got a job. She's starting with $1. They're going to double her pay each time. So we filled in all our tables here. And what did we say we were doing each day to get to the next number? Doubling it, which means times 2. How did we find out how much she made on the 10th day? Times 2. We just kept multiplying until we got to the 10th day, right? The next one is 350. So do you want to keep multiplying until you get to the 350? I would lose count after like 12. So what could we do instead? We need to find a rule, right? We got to find a rule that's going to work for this function. So let's brainstorm here. What do we think is happening? Well, look at these numbers. See if you can find a pattern.
You're squaring it's even numbers.
They're even numbers. Are we squaring it?
No, not. Because 3 squared is not 8.
You're on the right track.
Oh, okay.
What you think?
You're squaring, like, so like 4, you square it equals 16. 32, you square it equals 16. So it's in every other number.
But there were a bunch in here that we skipped.
That's how we know that. That's right.
Keep thinking. Keep brainstorming. What do you think? Is there any kind of pattern between the day and how much money you get?
Yeah. That too. No. I was going to look at the They're all doubling.
They're all doubling. Okay.
I really don't know.
So,
I have a feeling you're squaring something. I just don't know what.
is it squared each time though?
No.
So maybe your only exponent you could ever have is it 2? Is the only exponent you could ever have 2? Can that change?
Yes.
So what if we had the day was your exponent?
What?
By what? 2?
So what did we start with?
0. No, 1.
Well, she started with $1. They're on day 0. So something to the 0 power gave her 1, right? Okay, then on her first day when she started, something to the first power gave her 2. So what was the something? 2. So let's see if that pattern still works. So if we have 2 to the second power, what do you get? 4. But if you have 2 to the third power, so if we have 2 to the fourth power, can we try 2 to the 10 first? Just be sure this is right before we get like way out of hand.
Well, wait, then how do you know what becomes the
Wait, I forgot how to do that.
What do you mean? So our rule,
2 to the first
correct?
is 2.
Yes.
How do you know what
No.
it is divided
2 to the, yeah. So how do you know that base number?
Yeah.
It's whatever you start with.
Oh, so you're just doing 1.
So like on day 1, she got $2. Correct, right. So our rule for this, whatever she gets paid, is 2 to the exponent of how many days she's been working. Is that okay? So like if we wanted to check our number for the 10th day, you could do 2 to the 10th power, and what do you get? Do we know how to type that in our calculator?
Yeah.
To the little up button to the 10th, and we get 1024, which is the same thing that we had, right?
So it's 2 to the 350 pounds.
So if we do 2 to the 350,
I did it right, Judy.
holy cow, I want her job. She could retire after less than a year, right?
The number doesn't go.
I could already be living that retired life.
Thing, or is it just like made up?
So, I can't get that number in this box. So instead, I'm going to write 2 to the 350 so we know where all this stuff is coming from. Is that okay? Well, that's not what that is. Infinite. Don't get me started on infinity.
Is that like actual like thing that?
All right. So are we good with our rule here?
Yeah.
Yes, Manny?
Yeah.
Okay. So exponential functions always are going to have your variable in the exponent. That's what makes them exponential. So that's what happened here. So like our x was our exponent. So I want you to jot that down just so we know that if you have got an exponential function, exponential function, it will always have a variable exponent. So let's pretend if you have a function that looks like this, and you have a function that looks like this, which one of these is exponential? Left side or right side?
Your
Exponential functions have a variable exponent.
right side.
So left side or right side?
Right side.
Does that make sense? What would this side be? If your exponent is 2, we have a special name for it. You just take a test on it. Starts with Q. Quadratic, yeah. So just know the difference between those. So everything that we're doing now is going to have that exponent as a variable. So your rules, your exponential form is right here. Okay. So you've got y equals a times b to the x plus k. Most of the time that k value is not going to be there for y'all, so you don't have to worry about it a whole lot. The a is your initial amount, so whatever they tell you you're starting with. So in the problem that we just did, that was 2, because she started with $2 on her first day for her pay. A lot of the times when we are working these problems, it's talking about the value of a car or the value of a house or something like that. And the value is appreciating or depreciating. So, or like an investment, like if you put money in the bank. So that starting amount is sometimes called principal, especially if they're talking about money. So I want you to put that here as well. P-R-I-N-C-P-L-E. And when you go on to later maths, they're going to want you to know that that's called principal, not just where you start at. Okay, so your initial amount or your principal. And again, that's that A value out front. So then inside parentheses, we have your growth or decay factor. So that's just telling you like how big it's getting or how small it's getting and how quickly. So if it's growth, that B value is going to be bigger than 1. If it's decay, that B value is going to be less than 1. And it's really going to be between 0 and 1. It's not going to go negative. So we could put that in there if you wanted to. But you just need to know that growth is bigger than 1, decay is less than 1. Is that okay? Question? So all your exponential functions are going to share one key point, and that's the y-intercept. Because when you plug in a 0 for an exponent, what do you always get out no matter what? 1, right? So we're going to write that it's 0, 1. So if you're not sure what that y-intercept should be, how could you find it? If you don't have a graph, you just have the equation. How do you find a y-intercept? This is not linear, so there's not like a b. We know that y-intercept is where what equals 0? X. So just plug in a 0 for x. Y'all, I only mention this because it's going to be on your exam at the end of the year. There's going to be a big, long, crazy function that's exponential, and you've got to find your y-intercept. So you've got to plug in a 0 for x. That's how you do that. So make sure that you know how to do this. It will be on your exam that you take in 17 days. Yeah. Are we okay? All right.
17 days.
Class days. Question? Okay. That y-intercept may change based on your k value. So it could also be 0, k plus 1, and we'll talk about that more later, perhaps. Yeah, we'll do some more practice with that later. Remind me that we need to talk about this before you take your test for this unit. We'll do that, okay? All right, cool. So if you've got exponential growth, that means that your, like our pay up here, it got really, really big, really, really fast. That's exponential growth, okay? So other things you can think of is like bacteria. You know, bacteria, and like, you know how people, when somebody gets sick and then they're around people that are sick and then suddenly everybody's sick? You know how that works? Like that happened to us this spring. So that's getting like really, really big, really, really quick. So exponential growth. So you're always going to have that key point of 0, 1, and then it's going to shoot up really, really fast on the right side, and it'll level out towards 0 on the left. So it's never going to cross 0, it's never going to touch 0, but it's going to get super, super close. So like 1 over 100,000 as a fraction. So really, 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 really small, but never actually going to equal 0. And then it'll get really, 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 really big on the other side. So how do you think exponential decay might look different? The opposite, right? So it's going to start at a bigger number and then get small and get closer to 0 on the right, and it'll shoot up on the left. So essentially it's just the same thing, but flip-flopped. Questions? Alright, so let's grab some. So for the first one, we've got the function y equals 2 to the x, and we've already played with this a little bit with that girl at the top and her pay, right? So when you have 2 to the 0 power, what do you get? 1. I'm starting here because I think that the positive numbers are easier than the negatives, so we're going to handle that first. If you have 2 to the first power, what do you get?
2.
If you have 2 to the second power, what do you get?
4.
If you have 2 to the third power, what do you get?
8.
Is that all right? So this other part is going to be a little bit trickier. So we've got 2 to the negative 1. So do y'all remember what we do with negative exponents? Put it on the bottom. So we're going to have a 2 on the bottom as to the first power, right? Because we changed it so it's not negative anymore. And what's on top? So what is 2 to the negative 1? 1/2. Now we're going to have to graph this. So what might be easier to have right here instead of 0.5? So I'm going to put both. So what about 2 to the negative 2? What do you have to do with negative exponents? Put it on the bottom. So on the bottom of our fraction, what do we have? 2 what? Squared. And what's on top? 1. So what is 2 squared? Do y'all see a pattern yet? So when we plugged in a positive 1, you got 2. When you plugged in a negative 1, you had 1 over 2. When we plugged in positive 2, you had 4. When you plugged in negative 2, you had 1 over 4. So when you plug in negative 3, what do you think you're going to get? 1 over 8. So we could check that. So if you have 2 to the negative 3, what do you do with your negative exponents? Move it to the bottom, so we'll have 1 over 2 cubed. And what is 2 cubed? 8. Is that okay? Do we kind of see how that pattern works? We can, yep. So we'll have 1/8. What is 1/4 as a decimal? 0.25, think like quarters, yeah? And what about 1/8? That was a little bit trickier. So we did like 12.5, right? Half each time, yeah? So 5.5 divided by 2 is 25, divided by 2, 12.5 or 0.125. Does that make any sense? Because like if you look at your y values, we're just dividing by 2 each time if you want to go backwards that way. So 8 divided by 2 is 4, 4 divided by 2 is 2, 2 divided by 2 is 1, 1 divided by 2 is 1/2. Yeah, that's how that's working. And if you didn't know, you can just put it in the calculator. Questions on how we got any of those values right now? Are we okay? All right, so let's graph those. So I'm going to start at 0, 1. So 0, 1, we have a point. 1, 2 is a point, 2, 4 is a point, and 3, 8 is a point. And then those fractions, you're going to have to just do the best you can and make sure you're getting super, super close to 0, but don't actually cross 0. They're not going to be exact, and that's all right. And then we'll connect those, and we'll have our graph. Questions? So are we still okay right now?
Yeah.
So for the next one, we've got y equals 1/2 to the x. So how do we think this might change? Do you have any guesses?
Maybe. Hold on.
Let's see. What is 1/2 to the 0 power? 1. What is 1/2 to the first power?
Wow.
1/2. What is 1/2 squared? 1/4. So then 1/2 to the third would be what?
1/8.
So do y'all remember last time when we plugged in the negatives, it just like flipped it?
Yeah.
So what do you think it's going to do over here? So when we plug in a -1, what are we going to have? 2. When you plug in a -2, what are you going to get? When you plug in a -3, what are you going to get? Do you see how that works, y'all? Questions? So we'll plot those points. So we've got 0, 1, 1, 1/2, 1/4, 1/8. And so this one, since it's getting really small really fast, what could we call that? Decay, yeah. So the last part of the bottom of the page, it wants us to compare the two graphs and what differences do we notice. So what is the biggest difference? One is growth, one is decay. What else do we notice? So when you flip, do you remember what that's called? Specifically a fraction. Starts with the R. Reciprocal. So we could say that your tables are reciprocals. Do they have anything in common?
They have the same notes now.
0, 1. What's that point? When x is 0, what is it?
Why?
Your y-intercept. Questions? So if we're looking just at our tables, what is a pattern that you notice for these exponential functions? What's happening? Okay, so they're kind of symmetrical, kind of you just like flip it. What else do we notice? So they're either getting really big really fast or really small really fast. What did we say we were doing at the top to get her pay each time? Her pay was doubling, so to get to the next one, what did you do? Which means times 2. So you got that times 2 is your pattern for exponential functions. So on the back, we're going to look at tables or the rules and just decide if it's an exponential function or not. So if it's exponential, it's going to multiply by some number each time in your table. So for that first table there, looking at your y values, what are they doing each time? How do you get from 1 to 1.5? How do you get from 1.5 to 2? So they're adding 0.5. Are they doing that every time? Yeah. So they're adding some number each time. Is that going to be exponential? What do we say it means if it's exponential? Or what are they doing if it's exponential? So is this exponential? No, because they're adding some number each time. Do you remember what type of function adds something each time, or maybe goes up by the same amount each time? An L. Yep, it's linear. So if it's adding some number each time, that's going to be linear. So this would actually be a linear function. So when we plot those points, it's going to make a line. You could write it in like y equals mx plus b. For b over there, look at your y values. What are they doing each time? To get from 1 to 3, what could you do? From 3 to 9, what could you do? And 9 to 27, what could you do? So they're multiplying by some number each time? So is that exponential? Yes. And also, if we look at those y values, are they getting really big really fast? Right? So they're growing pretty quickly. If you look back at the linear one, were they getting big really fast or pretty steadily? It's just like a little bit at a time, right? Just a little bit each time. So we're going to talk about comparing the different functions next week. But an exponential function is always going to get bigger faster and exceed the value of your linear function at some point in time. So what I mean by that, I'm not going to sketch it on here just because we're talking about it. Your exponential function, do you remember what that looks like when we graph it? We just did it. It's like really big, really fast, right? What is a linear function going to look like when you graph it? Just straight. So at some point, eventually, even if the linear function starts off higher, which one's going to exceed the other? Exponential. And that's always going to be true, okay? So that's just something to be mindful of. And again, we're going to talk about that more next week. So looking at C, that function right there, we got y equals 3x squared. Is that exponential? How can you tell if a function is exponential? Exponential functions have a variable exponent. So does this have a variable exponent? No, what would this be? Your exponent is 2. We said it has a special name. It's quadratic. And what about the last one over there? We have y equals 3 times 6 to the x. Yes, that's exponential. How do we know? Exponential. Because your exponent is a variable. Questions? So are we all right so far? Anybody's mind like completely blown, doesn't even know what's going on anymore? Okay. You think it's cool now, you just wait. It's going to get better. It really is going to get better, I promise. That was the boring stuff. Alright, so suppose that we have 30 flower beetles and they're left undisturbed in a warehouse bin. The beetle population doubles each week. So what does that mean if it's doubling? If it is going to be exponential growth, how are you going to, what's your y values going to do if it's doubling? Times what? 2. The function to represent that is right here. So that 30, that a value up front, do y'all remember the a that we were talking about back here? That's what you started with. So we started with 30 beetles right there. And then 2, that's your growth. So we know that it's doubling. So anytime they say doubling, That means your number inside parentheses has got to be 2. What if they said tripling? What do you think it would be? 3. Quadrupling. Does that make sense? Yeah? So you're going to have to start building these functions later, so these are things that we need to start picking up on. And then your exponent is always going to be an x. So there's our function. They gave it to you, and it gives your population after x number of weeks. So how many beetles will there be after 56 days? Hold on. Our function is in terms of, they're asking us in terms of, so how many weeks are in 56 days? How do you get that? So 56 divided by 7 gives us 8 weeks. So to find out how many beetles there are going to be after 8 weeks, what do you think we need to do? Just plug in 8. So in your calculator, you're going to write 30, parentheses, 2, close your parentheses, to the 8th. Type that in exactly as we have it written. Let me know what you get. Holy cow, that's a ton of beetles. Isn't it?
Wait, are they using like flour, like a plant flour, or like actually like could be baking?
I think that, like,
Because it says beetles and then it says flour, like flour used for the cooking.
yeah, I'm not sure what a flower beetle is. I don't
Even
know.
a warehouse thing.
We'll look it up.
That's what I was thinking. They're like little, like, because my grandma's old house used to have them bad, and they're like little, like, brownish growing things, and like, they all in their boxes. Ew. That's nasty.
Ew, that's really gross.
And like at night, they come out all over your
I should get like a clip art picture and like add it right here of the beetles. All right, that okay? Are we good with everything we did there? Questions on anything? All right, cool. So the next one, initial population of 20 rabbits triples every half year. So there's your function. Why did they put 20 out front here?
Because that's how we started with.
That's how many rabbits we started with.
Principal.
Your principal, your initial amount. That 3 inside the parentheses. Why did they put a 3 this time?
Because it's tripling.
Because it's tripling. So there's your function. X is in the exponent. It gives it after X number of half year periods. So every like 6 months. So how many rabbits will there be in 3 years? So again, our function is talking about what? Half years, or every 6 months, right? But they're asking us about 3 years. So how many half years or 6 year periods are there in 3 years? 6, right? Because you're going to have 2 half years in 1 year, right? So what do we actually need to plug into our function? 6. So we're going to have 20, parentheses, 3 to the 6. Type that straight in your calculator. Let me know what you get. Can you imagine 14,580 rabbits? I mean, they're cute, but they be messy. My roommate in college had a rabbit. Just one. It was a mess. It threw the little shavings everywhere all the time. I had a little, like, fur rug. Have y'all seen those, like, the faux fur little rugs? And it, like, wanted to play on it. And I'm like, oh, okay, that's fine. And then it peed on it. And it was a white rug. So it was ruined. Anyway, that's a ton of rabbits. So exponential growth and exponential decay. What's going to happen with them? How fast? Very, very, very fast. Yeah. Have y'all ever heard, like, the phrase, like, what do they say? Is it multiplying like rabbits? Or something like that. That's where that comes from. Anyway, maybe y'all are too young for that. That's fine. I'm just old. All right, so the next one, value of a computer after a number of years is modeled by this function right here. So how much was the computer worth when we started? If this is our function. $4,000, right? So is the value of this computer going to get more? Is it going to increase or is it going to decrease? What do you think?
Decrease.
How do we know that it's going to decrease?
Because it loses its value.
Well, it's going to lose its value as it gets older, right? That's common sense. We know that, right? Because y'all are smart individuals. Do you remember on the front of the page where we said that B value, the number inside, if it's bigger than 1, it's growth, and if it's less than 1, it's decay? So that's where that's coming back to, okay? So since that number is less than 1, this value is going to decrease. Exactly. Yeah. So there's our function. It's after X number of years. So what will the computer be worth after 1 year? How are you going to find that out? How are you going to find that out?
4,000.
How do you find that out? Where do you plug in 1?
Put it in the calculator.
You put one or
Put one.
Because it's number of years. And we want to know after 1 year. So what do you do?
Plug in one.
Plug in 1. So plug in 1, and what do you get? 2,880. Is that okay?
Yeah.
So then how about after 5 years? How are you going to figure that out?
So plug in a 5.
Plug in a 5 for your exponent. So type that in your calculator. These are too easy for you to like not get, right?
$77.39.
Are you sure?
No, I got 7.73.
I got 7.
7E7.
I got 7.
Okay, let's take a look at this because clearly we're having some struggles. So that's what I got. No, does y'all have any in it?
Why does mine?
$77.40.
That's 773.
How did 77?
I don't know, guys. When you typed it in the calculator, did you do 4,000 with 3 zeros? Did we get that?
Yeah, I did that.
And
7.2, sorry.
then 0.72.
Yeah, I got 7.
Okay.
Oh, wait, no.
So
This is playing on to do the calculator. Oh, wait, I did that, just put them down.
this is talking about the value of a computer. So that's in money, right?
Yeah.
How many decimal places should we go?
2.
2. So what should we round this to?
97.
0.97. Is that okay?
Yeah.
Questions?
Wait, do other countries use different things for their money? But, or not, but obviously.
Currencies. What do you mean?
Like how we go like 2 for ours, do they go like 4?
No. Some of them might not have decimals at all.
They're just solid numbers. That would be so, can we just do that? That's so easy.
I really only know about like euros and francs. That's it. This is the only ones I've had. Yep, euros.
Right. Well, right.
The last part here. So, in how many years will it be? About $400. How do we figure that out?
You put 400 in for the 4.
We want to know in how many years it's going to be 400. So, is this talking about this? Is that a time, an X or a Y?
That's your X.
They're giving
No,
you
that's
a Y.
So you make it equal 400.
So on all the ones before, they gave us an X, so you could just plug that in. Now they're telling us what it's supposed to equal, and we have to figure out how much time it's going to take to get there. So we could set our equation equal to 400, but do you know how to solve that?
No.
You won't learn how to solve that till like pre-calc, okay? So you got a while before you get there. So we're going to do something else instead. I'm going to turn it off. Grab your calculator, and we're going to go to a graph. And we're going to type in our function. So be careful when you're typing that in. Make sure you have 3 zeros and 0.72, not anything else.
Yeah.
Wait, do you put it?
Yep, and you just put X for your exponent, just like you would type in any other function. When it's got variables in there, you just type them in. And then we'll hit enter. And we can't see anything, but that's okay, because I want to look at the table, because I want to see after how many years, what does it equal? Yeah? So how do we get up our table? Control T. So we see after 2 years, there's the price. After 3 years, there's the price, etc., etc. What do we want to look for? 400. So when is it closest to 400?
7.
After 7 years. Is that okay?
This is fun, just very complicated. I mean,
Well, we're just getting started, so you got plenty of time. We're okay. Questions? Are we all right now? Did that make sense to everybody? Is there anything we're not sure about? Don't understand how we did it? All right, then we'll move on to the next one. So number 4, we've got a new function this time. It's going to give your country's population, where T is the number of years since January of 1995. So when T equals 0, that's in 1995. So when we have T equals 1, what year would that be? Right? right? Does that make sense? So our time is starting in 1995. So if our answer, if we get like 5 for t, is it actually 5? Or what year would it be? 1995 plus 5.
2000.
That makes sense? Are we kind of okay with that? You're going to have a lot of problems like this. So this little statement right here is super important, okay? So if they're telling you it's years since whatever, that's where you start. So our first part here says, according to the function, what was the population of the country in 2004? So our function starts in 1995. So how much time has passed from 1995 to 2004?
9 years.
So what is t going to equal?
9.
9. So we're not plugging in 2004, but 9. Yeah? So you're going to plug in a 9 for t, and that'll give you a number, and that'll be our answer there. So when you plugged in 9, what did you get out?
76.
37.
77.
Is that okay?
Yeah.
Questions on that one? All right. So the next part, what is predicted by the function for the population in 2016? So it wants to know what's the population going to be in 2016. Can we just plug in 2016? What do we have to find out? How much time has passed? So from 1995 to 2016, how many years have gone by? 21. How did you figure that out?
I subtracted.
You can just subtract, yeah. So it's not always going to be like super easy to find. So just subtract if you're not sure. So we did 2016 minus 1995, and that gave us 21. So then you're plugging in 21 to your function, just like we did before with the line. And what do we get this time? 0.2. Is that okay? Questions there? Is everybody still okay? All right. So in what year was the population closest to 75 million? Now this is already in millions. So how are we going to figure this out? When is it closest to 75? Where do we look? In the table, right? So this is just like the one before, where it wanted to know when it was worth $400. We want to know when our population is about 75. So you'll look in your table to find that. So we need to graph it and pull up the table. So let's see, when are we close to 75? What do you think is closer, 8 or 9? Do y'all agree? Because 9 is 76.6 essentially, and 8 is 74.4. So the 8 is going to be closer to 75. Is that all right?
Yeah.
Okay, so after 8 years, what year would it be? 1995 plus 8 gives you 2003. Is that okay? Questions there? I can't tell if we're quiet because we don't understand or because we're bored. So, sorry. All right, last one. 3 years ago, Andy invested $5,000 in an account that earns 5% interest compounded annually. The equation right here describes the balance in the account where T is time in years. Andy made no additional deposits and no withdrawals. So, how much is in the account now? When did he set up his account? So how long has money been in there? So what are you plugging in? 3, because it's been in there for 3 years. So plug in 3. So say T equals 3, plug that in, tell me what you get. Wait, how many places should we go? 2, because it's money, so 1, 3. How much is going to be there after 10 years? What are you going to do? Plug in 10. So t equals 10 this time. Plug that in. What do we get there?
8,000.
And the last part, after how many years will it have about $25,000? Where do you look? In your table, and we want to see when the Y value is about 25,000. You may have to scroll a little bit. So what do we think? Or what did we find? About 33? Did we get there? Yeah. Questions on anything?